On July 20th, 1969, the Apollo program sent humans to the moon for the very first time. When the astronauts walked on the lunar surface, they left behind something that wasn't just a flag or a footprint. They placed a special set of tiny mirrors on the moon. Scientists on Earth pointed a powerful laser at those mirrors.
Preparing to fire laser at the moon.
Make it so.
And even though the moon is almost 400,000 kilometers away, a little bit of that laser light bounced off the mirrors and came all the way back.
There, we'll measure the photons that return and let us see it on this computer. Raj, get them some glasses.
There it is. There's the spike.
2.5 seconds for the light to return. That's the moon. We hit the moon.
By timing how long the light took to return, scientists could measure the distance to the moon with incredible accuracy, down to just a few centimeters.
The fact that we can do this is the only way of definitively proving that there are man-made objects on the moon, put there by a member of a species that only 60 years before had just invented the airplane.
What species is that?
And Leonard was absolutely right. But beyond that, the experiment also revealed something beautifully simple. Light always follows the same rules, whether it's bouncing off a mirror on your desk or a mirror sitting on the moon. Light behaves a bit like an excited kid on a trampoline. Whenever it hits a table, a lake, or almost anything with a surface, it bounces back. That bounce is called reflection, and that's why you can see things that don't glow. Your backpack, your dog, even the moon, because reflected light zooms straight into your eyes and says, "Look at this." Light doesn't just bounce however it wants. It follows a pattern, and you get to uncover it like a detective. Put a flat mirror on the table. Stand a piece of cardboard on the mirror like a tiny wall. Draw a line on the cardboard that points perpendicular to the mirror. This is like the center line for your investigation. Shine a beam of light so it hits point O on the mirror, and this is our incident light ray. Watch it bounce off in a new direction, which we call the reflected light ray. Trace the path of the incident light ray and the reflected light ray. Change the angle. Try it again. Use different colors so your cardboard turns into a colorful map of light's adventures. Take away the cardboard and measure the angle of incidence and the angle of reflection with a protractor. When you fold the cardboard forward or backward, you might notice something very interesting. Sometimes you can see the reflected light on the cardboard, and sometimes you can't. What pattern did you discover about how light reflects? Imagine a line standing straight up from the mirror at the point where the light hits. That line is called the normal, more specifically the normal to the surface. The angle between the incident light and the normal is the angle of incidence, labeled theta sub I. The angle between the reflected light and the normal is the angle of reflection, labeled theta sub R. From our experiment, we can sum up light's behavior like this. The incident light ray, the reflected light ray, and the normal all lie in the same flat plane. The incident light ray and the reflected light ray sit on opposite sides of the normal. And the big rule, the angle of reflection equals the angle of incidence. This is the law of reflection, light's official bounce rule. You've probably seen a billiard ball bounce off the edge of a pool table. It behaves just like light following the law of reflection. Does that mean that light is made up of tiny, invisible particles? If you send a beam of light backward along the same path as the reflected ray, it will bounce off the mirror and travel back along the original incoming path. This shows that light paths are reversible. You see this in everyday life, too. If you can see your friend's eyes in a mirror, then your friend can definitely see your eyes in that same mirror. Light is playing the same back and forth game for both of you. Imagine sunlight hitting a mirror. If you look in the direction the mirror sends the light, it feels super bright. But if you look from other directions, you don't see that blinding light at all. Now, try that same thing with a piece of white paper. No matter where you stand, the paper looks bright, but it never hurts your eyes. Why does the mirror act like a spotlight while the paper acts like a gentle lamp? A mirror is extremely smooth. When a bunch of parallel light rays hit it, they bounce off in neat parallel lines, like a team marching in perfect formation. This is called mirror reflection, or more scientifically, specular reflection. But a piece of white paper, even though it looks flat, is already full of tiny bumps and dips if you zoom in with a microscope. When light hits this uneven surface, the rays bounce off in all different directions, like a crowd scattering after recess.
No.
This is called diffuse reflection. Because objects like tables, chairs, books, and walls all have slightly bumpy surfaces, they scatter light in many directions. And that's why you can see them from almost everywhere in the room. You have reached the end of this episode, and this is Dr. Walden from Graceful Science. Thanks for watching.